you very much. Thank you to the organisers for the invitation to this excellent workshop. Really enjoyed it. So I'm going to give a talk that is going to be an overview of several different pieces of work we've done using linear scaling DFT and spectral function unfolding, and we applied it to various different systems. So it'll be a bit of a whistle-stop tour. I took several things out, but then I put them back in because people at this conference had talked about them, and I thought it was interesting to make the connection. So what's the reason, the motivation here? Well, traditional DFT encounters serious problems when we try to apply it to 2D material heterostructures. As I'm sure anyone who's tried to simulate a heterostructure with an incommensurate lattice parameters, as soon as you can only model them by making a commensurate approximation to the interface, and then you still need to strain one layer or both layers to make an exact match. And what this means is that models of 2DM interfaces require very large supercells in order to keep the strain low. And yet the band structures of many 2D materials are very sensitive to strain, so you have to keep the strain very low. And typically a model that keeps a strain below some target that you might have in mind for not damaging the band structure too much may well end up demanding that you have a system which is well beyond a length scale accessible to traditional DFT. And bear in mind, of course, that traditional DFT scales as the cube of the system size. So we have to work very hard to find particular angles in some cases that can make the calculations accessible to traditional DFT, and that limits what we can do. It's also non-trivial to find these supercells in the first place. You have a space of 8 integers and a twist angle to play with. So finding coincident cells, particularly for multi-layer structures, more than 2 layers, is rather hard. So and then on top of that, we have this problem of how does one actually go about making useful comparisons of band structures between the large supercell interface models and the primitive cell. And the answer to that, as has been known for a few years, is spectral function unfolding. So just to recap what's wrong with traditional DFT. Traditional DFT is a theory that works on the basis of diagonalizing a Hamiltonian, finding eigenstates of a Hamiltonian which span the whole system, and it has a scalability problem in that the computational effort required is inherently cubic scaling the system size, and this becomes well known to become unfeasible beyond around, depends on the system, but something like 400 to 800 atoms, and we often need to do larger calculations to enter a realistic regime for 2D material heterostructures. So the way around this is to work with not with the eigenstates themselves, but with a composite object that sums them up, the single particle density matrix. And so over the last 15 or so years, a lot of effort has been put into the development of linear scaling DFT codes, which work in terms of local orbitals and a density matrix description, and then exploit the nearsightedness of quantum mechanics in order to truncate that density matrix representation. So if one does that, we can put together a package like ONETEP. ONETEP is a linear scaling DFT code, which works in a basis of so-called non-orthogonal generalized Fourier functions. These are local orbitals that adapt in situ to their local environment. And by optimizing these in situ, we can have a very small basis, only typically a small number per atom, 9 or 13 or so for metallic, for semiconducting TMDCs, things like that. And we optimize them in situ, expressed in a systematic basis of p-sync functions. So it's equivalent exactly to plane wave results if one plays with the parameters enough. We have a double loop optimization scheme, which means we optimize both the kernel and the NGRFs. So what kind of things have we applied this to? Well, in the area of 2D materials, we've been working on this for quite a few years now. We started by looking at transition metal chalcogenide bilayers, heterobilayers, and in this case, we found we needed various new bits of technology, the van der Waals functionals, the POW and spin orbit coupling, which we now have in ONETEP. And just for kind of calibration of your expectations, a rough feasible limit is anything up to about 10,000 atoms or so is a feasible single point DFT calculation, and maybe something like 4,000 to 5,000 atoms for a juncture optimization. It's not cheap, but it's accessible at least for these tools, whereas it's not for traditional DFT. So as I say, we had to make use of spectral function unfolding, which allows us to fold back the spectral function from the to unfold the spectral function from the supercell Brillouin zone back into to the primitive cell of each layer, and so you can directly compare the kind of before and after. We can make some nice images by looking at the kind of before and after associated with hybridization of a heterostructure. Okay, so what we did back, I'm just going to skip over a few slides on our early work with this. Back in 2015, we looked at hybridizations in MOSE2, MOS2, looked at the variation of the whole mass. And then we started working with various experimentalists, including Neil Wilson's group at Warwick. And we were able to compare then directly to micro-ARPES results. And this micro-ARPES results effectively represent a direct experimental probe of the band structure. And so they were interested at the time in TMD multi-layer and heterobilayer systems. We managed to show that the DFT results could be, at least in the first few bands away from the Fermi level, could agree very well with this micro-ARPES and demonstrate very well that the hybridization and the spin orbit splittings were very well matched to experiment. And so that then allows us to move on to work on heterobilayers. The group of Xiaodong Zhu and David Cobden in Washington were fabricating these systems like WSE2, WS2 heterobilayers, and we were able to kind of reproduce the hybridizations and the changes in effective mass upon the construction of this heterobilayer. And another quite interesting result we showed back in that paper was where we had intentionally aligned structures, intentionally low mismatch structures. We could get this coexistence of commensurate and incommensurate domains, and we could see this through the fact that those different domains had different interlayer distances and therefore different hybridizations, and the combination of DFT on the monolayers with DFT on the commensurate heterobilayers, and just superimposing them in the way that we knew how to do from the linear scaling calculations, allowed us to understand these band structures and show how these three bands is what you'd expect from the fact that there were pairs of two bands superimposed, but two of them were sitting on top of each other. So that was work we published back in 2017. And it also allowed us to extract band parameters and use the linear scaling DFT to align those systems. And in that paper, they also demonstrated the intralayer exciton in that system. We also worked on control of Fermi level by gating and reproducing reproducing the band structures associated with these gated structures, and showing that you could populate the conduction band, and that in fact GW calculations in this case were a very good reproduction of those results. And another area this spectral function unfolding has been very useful in is understanding the behavior of alloy systems. This is some recent work on niobium doped tungsten disulfide, where the STEM imaging has revealed that the doping is not isotropically distributed. They have a strong anisotropy associated with growth fronts, and we've been able to use this spectral function unfolding to understand the band structures you get in these systems, looking along the direction of the line in the band structure plot, this gamma to M direction. We show as we go from a random system through to slightly more ordered and then to a perfect system, with this real system in the middle having been taken from a realistic region of that image. We show that we can evolve towards a greater amount of anisotropy in both the band structure and the predicted conductivity. We have this very strong conductivity ratio between the two directions. Okay, we also looked at post-transition metal chalcogenide materials like indium selenide. They're of great current interest. They're another system where we get this indirect transition as we change the layer number. We also see this this kind of Mexican hat behavior, which where the valence band dips around the gamma point. And this brings about the possibility of interesting band structure manipulation through hybridization. In this case, we kind of came to the project as it was quite advanced already, and we were investigated the possibility of building one of these structures. We actually managed to knock together a system with exactly the same misalignment angle and a relatively small supercell that was feasible to study. And we were able to show with that we were able to explain some of the unusual behavior they'd picked up in RPES on this graphene encapsulated INSE. They'd seen these kind of anti-crossings, and they were associated with anti-crossings in the INSE band. We were able to confirm that they were associated with hybridizations between the INSE and the graphene that take place outside of the first Brillouin zone of the INSE. And therefore we get this kind of umklapp hybridization. So we can see it quite clearly if we superimpose the band structures of the individual models and then compare that to the actual band structure of the heterostructure folded back into the Brillouin zone of the graphene in this case. So that's more than one copy of the Brillouin zone of the INSE, because that's got so much smaller a Brillouin zone. So what we see here is in the heterostructure, we can generate kind of non-local hybridizations. You see these band crossings away from where the actual intersection of the bands is in the graphene Brillouin zone, and these are from kind of periodic images in subsequent Brillouin zones of the INSE. And we can fit to a avoided crossing model and show that actually generates very good predictions there of for the coupling. Okay, so I've got a video of that, but I don't think I've got time to show that. That work. You can also look at slices through the Brillouin zone generated by kind of mirroring that path sixfold around the ring, and it compares very well to the RPES constant energy slices. Okay, just the last thing I want to talk about very briefly is work by Charmaine Lowe on the twisted INSE bilayer. She's been able to show this angle dependence of the hybridization here. We get a kind of split off band emerging as a function of twist angle. So just in conclusion, linear scaling DFT with ONETEP can let us do plane wave DFT quality simulations of layered material systems comprising thousands of atoms. And it allows us a direct window on band structure effects in heterobilayers. We don't have to kind of put together complicated models where we allow the band structures of the individual components to hybridize. We can just design a system from scratch that is the interface and has effectively no strain. And then we can predict these kind of, you can project back into the primitive cells of the individual layers and understand these hybridization, effective mass tuning, band splittings off, and kind of separations. And we can identify interesting effects like these umklapp scattering events that can cause ghost hybridizations. So there's a whole kind of world of possibility for manipulation of the band structure in these materials, as we've seen in many of the talks this week. And hopefully this allows DFT to access those without particularly great challenge. I'm hoping soon to release a Python package 2DM toolkit, which is going to be centered around structure building and spectral function unfolding plotting. So look out for that if that's something you're interested in. Okay, I'd like to thank various people who've been involved in this episode for funding, and all the various people who've contributed to the theory and experiment behind this work.